So today we are talking about Fibonacci. Who does know Fibonacci? Okay, so before I start talking, I would like to show you a short video that introduces the today lesson. So today we are going to talk about Fibonacci, that is math arguments, but like in this video, we can talk about Fibonacci even all around us. So Fibonacci is everywhere, in the nature and the art, for example, so not only in math lessons. So who is Fibonacci? Our story starts from Pisa, that is a town in Tuscany, and Fibonacci was born in 1170 from a merchant family. So his father bought and sold with the Orient, and for example Indian populations or China populations. So Fibonacci was educated with a mathematical base, and he started to learn Arabian figures and Hindu figures. So he knew zero, for example, and he started to write some books. For example, he wrote Liber Abaci, that is a really important book, because inside it he wrote all his knowledge about Arabian and Hindu figures. As I before said, for example, zero, that wasn't still used by European people. So then even in the time after him, for example, Leonardo da Vinci, who is more famous, talk about him as a person who was very important. So it's a very important person. On the background we have a picture of Pisa at that time, so 1170, and I read that in this period in Pisa there's expositions of Fibonacci and Leonardo da Vinci, and the importance of commerce with the Orient. So it's connected to these types.
So I'm going to talk about the Fibonacci sequence. The Fibonacci sequence posed and solved a problem that it was about the growth of population of rabbits, and the solution, generation by generation, was a sequence of lots of numbers that in time that is called the Fibonacci numbers. And there was a problem that rabbits are able to mate at the age of 1 month, so that at the end of the second month, a female can mate another pair of rabbits. And in the problem, rabbits never die, and every month there is a new pair of rabbits. And there was a question which was how many pairs will there be in 1 year. So he starts at the end of the first month, and the first pairs of rabbits made only one pair. At the end of the second month, the female produced a new pair of rabbits, and so at the end of the second month there were two pairs of rabbits, and at the end of the third month there were the original female of the first month made a second pair, so there were three pairs of rabbits, and so on. At the end of the number x of month, the number of pair of rabbits was equal to the number of new pairs and plus the number of pairs alive last month. Yes, at the end of the numbers. So another thing that is written in the Fibonacci was the Fibonacci sequence of numbers, and that he began to sequence from 1 plus 1 is 2, but in our days mathematicians starts to calculate with 0, 0 plus 1 plus 1 plus 2, and so on. Fibonacci carried the calculation up to the 13th place, that was 233, and but in another manuscript we found that he carried on until the place of 377. He created also the Combinatorial Identities, which talks about the identities involving Fibonacci numbers, and he proved using combinatorial arguments, using the fact that Fibonacci's number can be expressed like the number of sequence of the first and second, that's some n, which is the every number, minus 1. This can be taken as the definition of Fibonacci's number, with the convent that f0 is equal to 0, meaning no sum adds to the number minus 1, and f1 is 1, meaning that sum adds to 0. And with the combinational identities, the order of the summand matters, because, for example, the calculation of 1 plus 2 is different for Fibonacci than 2 plus 1. So he considered two different calculates, and for example, so in the first group, the remaining terms to n minus 2, and in the second group, remaining terms to n minus 3. So there are f n minus 2, sums, So there are a total of fn minus 1 put together to show the equal of the calculates of the summing. And so in the end, I think that specifically the first group consists of the second group. Those start with n plus 2 that start 1 plus 2, the third 1 plus 1 plus 2, and so on until the last group.
So this sequence, Fibonacci sequence, is special for different aspects. For example, there are lots of similes or properties. For example, the square of every Fibonacci number is different from the product of the two numbers next to it. Less just plus 1 unit. For example, we have the Fibonacci, in red we have the number of the Fibonacci sequence, and for example we have 3, that is the square is 9, and we have 2 pair 5, and we have 10, and the square of 3 is 9. So 9 plus 1 is 10. So the product of the two numbers next to it. Okay. Another aspect of this sequence can be that if we summarize the number, a number that we can choose of Fibonacci's figures of the sequence, it's equal to the number n, so the number of figures we choose, and plus 2. For example, we have 1 plus 1 plus 2 plus 3, that is 7, and we have for example, 1 plus 1 plus 2 plus 3 plus 5, that is 12, and we have 13, the number 13, that is 12, that is 5 plus 2. So the number of figures we have summarized plus 2. So this sequence is special for this aspect. There are lots of properties that could be told, but these are some of the most, if we want to say it simply, and more understanding. So, as I said before, Fibonacci is everywhere. So we can have a relationship with the nature or art. For example, we start from the nature. If you see all this picture, like here together, we can say, what do they have in common? Fibonacci, obviously. So, for example, we have a nautilus that is shell. It's the shell of a mollusk that has a strange shape, because that's the shape of called logarithmic spiral that we are going to talk in the next lesson. And it's linked to Fibonacci sequence and Fibonacci's number. Or we have, for example, fruit like ananas or piñas that have spirals. For example, in ananas, the green lines, blue and red lines are the way of the spirals that turn all around the ananas. And if we count the squame of every spiral, we obtain Fibonacci's number, the same with the piña. And another interesting aspect is how leaves are put on stem of a plant or a flower, because scientists until, for example, Galileo, so in ancient times, started to study this plant stem, and they found that there's a connection between most of them. For example, we know that leaves in a plant try to their position is follows a circular and spiral way. So this is because plants need lots of light and sun. So the leaves that are the part of the plant that catch the sun are putting in this way, so the sun can arrive in more quantity. So these spirals are connected between them by Fibonacci sequence, because the number of leaves that goes to the first position to a whole turn, so when the leaves return at his first place, it's a Fibonacci number. Another natural aspect of that we can find in natural Fibonacci sequence is in sunflowers, because inside them there are like spirals that are linked by Fibonacci's number. So it's like ananas, it's like piña, but inside the flower. So that's the thing. We can have the Fibonacci even in art. For example, in the first picture on the left, we have the distance between the two bigger columns, and we divide it per the distance between the left column and the distance that goes to the left column to Jesus Christ. Thank you. So we will obtain a Fibonacci number. Another paint is Mona Lisa, and here we have lots of Fibonacci referments. For example, on her face, if we put a rectangle around her face, we will obtain a gold rectangle. And if we put two rectangles around her body, so from the neck to her hands and from the dress to the bottom, we will obtain two gold rectangles. So even Leonardo used Fibonacci because he recognized that he was an important figure for mathematics at that time and even today. The third picture is the Uomo Vitruviano, that we have to consider his belly. So Leonardo said that the figure of a person is beautiful when the belly is it's in a distance that Fibonacci calculated. So if we calculate the distance between the head and the belly to the feet, it represents the Fibonacci numbers. Have you got some questions? So I had a video, but there isn't internet. So we will show you after to close our presentation about Fibonacci. So we hope that you can understand the importance of Fibonacci, because even if you don't like math, you can find interesting this argument, because even in nature or art, something that you can think that it's not connected to math, you can find math. So it's important, and I think fascinating how math can be everywhere, even if you don't like math. So I hope you enjoy it.
Today we are going to talk about Fibonacci sequence in music. But before doing that, I think we should have some short lesson about music in general that will be helpful for us.
To understand better the Fibonacci sense of music.
Yeah. So, for example, here we have a part of a piano keyboard. We have a white case and black case, but don't look at black ones, just look at the white ones. Under each case we have two letters that indicate the note that that case produces. So we have Do, Re, Mi, Fa, Sol, La, Si, and then again Do, Re, Mi, Fa, Sol, La, Si, and so on. These are the 7 notes, and we could repeat them infinity times. So for example, you could say, but here we have 1, 2, 3 times Do, and it isn't, but it isn't the same note, because the first Do is the second Do is higher than the first one. We could say the note is the same, but it changed the sound. Here we have the note in the pentagram, which is the structure that, where we write the notes. And you could see that we have 3 Do's, 1, 2, and 3, but they are written in different spaces. Now, rhythm in music on the top. We have to think about rhythm in music as a lot of cakes, one after the other. Each cake is called a pattern. At the beginning of each score, we can find a number. That number indicates us in how many parts we have to split our cake. For example, here we have a pattern, a cake, split in 4 parts. Each part is called beat. The white note indicates us that we have to hit 2 parts, so the note will last 2 beats. Under we have black notes. The black note indicates us that we have to hit only 1 part of the cake, so the note will last 1 beat. So we will need 4 beats to eat all the cake, or to complete the pattern. You can see so that we could have some combinations. For example, if we have some cakes split in 3 parts, we could have 3 black notes, 1 black note and 1 white note, or 1 white note and 1 black note. So you could say, but how many combinations do I have? To find a way of combination I get, I have to take the Fibonacci sequence. 3 is the number of bits of the pattern, so I have to take the first plus 1, so the fourth number of the Fibonacci sequence, which is 3. In fact, we have 3 combinations. Another example, for the pattern of 4 bits, we have 4 plus 1, so we look at the 5 number of the Fibonacci sequence, which is 5. So we have 5 combinations, as you could see.
Now we take about a different aspect of Fibonacci in series in Occidental music. For example, this is a study who is conducted by a Hungarian musicist, but we will say it later. And we start. We assign a note for every number of Fibonacci series. For example, I don't know if we prefer use the Occidental nomination on the Anglican nomination of note, Do or Si. Which you prefer? Do, okay. For example, Do, we assign the number 1. Re, we assign the number 2. Mi, number 3. Fa, number 4. Sol, number 5. La, number 6. Si, number 0. But in Fibonacci the numbers are bigger than 5, 6. So to convert every number into a note, we use a math operation, the model operation. And with that we recover numbers between 0 and 6. The model operation is, for example, when we read hours and we arrive at the 24, and after we restart to 1, 2, 3. So in this way we get a series composed by 16 numbers, which is infinitely repeated. For example, 1, 2, 3, 5. The number 8 become number 1, number 13 become number 6, number 21 become number 0, and so on. And we obtain this series.
8 in 1, we have to do this operation. We
dividing by 7, and the rest
is 1. So the number which we write is 1.
13 divided by 7 is 1, the rest is 6, so we obtain 6.
And so on.
This is the series 1, 1, 2, 3, 5, 1, 6, 0, 6, 6, 5, 4, 2, 6, 1, 0. We can see it's infinitely repeated because we tried for lots of numbers. And we transform the notes. We have assigned the notes in a pentagram, in a score, and we obtain this sequence. And this is the sequence type. If we change length of some notes and height, we will get a melody called first melody, and this melody is very important in music. And let's listen. And this is an example. Some musicians use this first melody, for example, and create a canon A canon is when we have lots of instruments, in this case 4 instruments, and do the same melody but starting a different time. And this is, in my opinion, very right. All this canon is based on Fibonacci series, and it's fantastic. This study is based, for example, started by some composer, for example, Bela Bartok and Arnaud Lemdai. We studied the possible relationship between series of numbers and music. The first one.
Bela Bartok is one of the most important Hungarian composers. He was born in Hungary in 1891 and he died in New York in 1945. He studies at the gymnasium and he was an excellent student of math and physics, but he also loved music. In fact, in 1899, he get part of the academic music in Budapest. And so the president of this academic music was Liszt, another great composer, Hungarian composer. So Bela Bartok also in his life always tried to compose compose music which had folk relationship. Hungarian dances, Romanian dances, and so on. He loved folk music. One of his most important compositions, in fact, is Romanian dances, and all his life he tried to improve this folk music, and he also did that. Yes, he is considered one of the greatest Hungarian composer, along with Franz Liszt, which was the president of his school.
Fibonacci's Bartok studied Fibonacci, and for example, he thinks Fibonacci is a natural sequence because we just seen nature is in nature there are a lot of references by Fibonacci, and he thinks the music based on Fibonacci sequences is a natural music. Is for us is better listen a natural music. For example, if music is based in Fibonacci sequence, Bela Bartok thinks it isn't possible. The music is boring. And there are another composition by Bela Bartok called The Fall of Icaro. This is a particular composition because Bela Bartok respects some study we have just seen, but there are also a study of Fibonacci in the time of Massimo. Because we will see after a determinate number of seconds the melody changes, And this number of seconds is a Fibonacci number. For example, se adesso può partire. Esempio, start.
So we saw that the composition lists 144 seconds, which is a number of Fibonacci. Now Erno Lenvai. Erno Lenvai is another Hungarian composer. He was born in Kaposvár in 1925. Kaposvár is a city in the southwest of Hungary, and he died in Budapest in 1993. Well, all his life long he studied Bela Bartok compositions, and he also used Fibonacci and the golden section in music. Also, often to define the musical interval in his composition. For example, we can see in these patterns that the gap between this note is 3, 2, 3, 5, or in another pattern 8, 2, 3, and 5. All these numbers are number of the Fibonacci sequence. Another interesting fact is that Lenvai used the Fibonacci numbers to put the dynamics in his compositions. Dynamics are, for example, forte and piano. For example, in the beginning of a score, he wrote piano, and then after a number of patterns, which is a number of Fibonacci, he wrote forte. So that's interesting. And the composition could be very strange because also Lenvai often did some experiments to link mathematics with music. So sometimes it was a little bit strange to listen to these compositions. Now we have Deep Purple. Well, Deep Purple is one of the most famous rock group ever. They were founded in 1968 by Chris Curtis, which is the drummer of the band. They were some guys of London, and since 1968 they've always produced a lot of songs which have been very, very successful, and they have always been at the top of the European and American charts. Their most famous songs are, for example, Smoke on the Water, I Will Start, Born, and also Child in Time. Child in Time is a particular song. It's one of their most famous songs. It's very beautiful, but maybe no one knows that in this song, Purple used the Fibonacci sequence. In fact, the song is structured in measure by 3, 5, and 8. So it's a little bit difficult to understand that. But even if you don't notice the Fibonacci sequence, just listen to this song. It's very, very, very good. If you listen carefully, we notice that the music is based on 3 plus 5 plus 8 plus 5 plus 3. And then again, 3 plus 5 plus 8 and so on. It's interesting. It's hard to understand. Yes.
We are going to show you the video. This is here is talking mathematics that talks about Fibonacci numbers in a, I think, in a pleasure way. So it's different probably from other lessons, other math lessons. It's in English with the subtitles.
So why do we learn mathematics? Essentially for 3 reasons. Calculation, application, and last, and unfortunately least, in terms of the time we give it, inspiration. Mathematics is the science of patterns, and we study it to learn how to think logically, critically, and creatively. But too much of the mathematics that we learn is
the question before of gold rectangle was the rectangle that was composed of the areas of the smaller square of every Fibonacci numbers. And so that was the video, and so if you've got some questions or